What specific problem does the new method aim to solve?
The new method aims to solve the problem of limited scalability in speech decoding models by leveraging unlabeled data and developing domain-specific self-supervised pretext tasks for representation learning with brain data. The method addresses the challenge of training models on collective internet-scale data by overcoming limitations such as the scarcity of labeled data, individual differences in brain data, and the lack of generalization across subjects and experiments. By pre-training on unlabeled brain data using pretext tasks like band prediction, phase shift prediction, and amplitude scale prediction, the method aims to improve downstream performance in speech detection and voicing classification tasks. Additionally, the method aims to enable cross-dataset, task, and subject generalization, ultimately scaling up speech decoding across multiple subjects, studies, and unlabeled data.
How does the proposed method or algorithm work? Illustrate step by step.
The proposed method works by first introducing a set of domain-specific self-supervised pretext tasks for representation learning with unlabeled brain data. These tasks include band prediction, phase shift prediction, and amplitude scale prediction, which aim to learn generalizable speech decoding features. These tasks are designed to be agnostic to the number of sensors in the signal, allowing for scalability across different datasets. During pre-training, these tasks are combined to create an augmented input for each task, and the network backbone is used to predict the transformations, resulting in a final pre-training loss. The neural architecture consists of a two-stage network, pre-training and fine-tuning stages. In the pre-training stage, a two-layer feed-forward projector is used to align the pretext and downstream tasks, followed by linear classifiers for each pretext task. In the fine-tuning stage, classifiers for the downstream tasks are introduced, and the model is trained with labeled data using shallow or deep fine-tuning approaches. Additionally, subject conditioning is incorporated into the model to account for individual variation in neural responses between subjects. The method leverages unlabeled data from the CAMCAN dataset for pre-training and fine-tunes on labeled heard speech MEG datasets for speech detection and voicing classification tasks. The experiments demonstrate that the representations learned with the pretext tasks can scale downstream performance with unlabeled data, showing improvements in accuracy as the amount of unlabeled data increases. The method also showcases generalization across datasets, subjects, and tasks, outperforming supervised baselines and demonstrating the effectiveness of self-supervised learning in improving downstream generalization.
What are the theoretical or practical benefits of using this method?
The theoretical and practical benefits of using the method described in the paper include the ability to scale speech decoding across multiple subjects, studies, and unlabeled data, leading to improved generalization in brain-computer interfaces. The method leverages self-supervised learning with pretext tasks tailored to neuroimaging signals, allowing for representation learning without the need for extensive labeled data. This approach enables the training of models on collective internet-scale data, addressing the limitations of individual subject datasets and facilitating cross-dataset, task, and subject generalization. By pre-training on unlabeled data and fine-tuning on labeled data, the method demonstrates improved downstream performance in speech detection and voicing classification tasks. Additionally, the method showcases the potential for generalization to novel subjects, highlighting the robustness of the learned representations. Practically, this method offers a pathway to scaling speech-brain-computer interfaces by utilizing diverse datasets and unlabeled data effectively, ultimately enhancing the efficiency and effectiveness of speech decoding systems in real-world applications.
How is the method validated or tested?
The method is validated or tested by evaluating the representations learned with pretext tasks through measuring their ability to scale downstream performance with unlabeled data. This includes assessing how well the representations can generalize across datasets, subjects, and tasks. The evaluation is focused on MEG data, which has better spatial resolution than EEG and faster sampling rates than fMRI. The experiments use CAM-CAN as an unlabeled representation learning dataset for pre-training and 2 labeled herd speech MEG datasets for fine-tuning. The pre-processing involves filtering the data, downsampling, and handling bad sensor channels. The downstream tasks of speech detection and voicing classification are used to assess the effectiveness of the method. The training process involves pre-training the models to completion and then shallow or deep fine-tuning on labeled data for each task. The results are compared to baselines, including randomly initialized models and supervised classifiers, to demonstrate the effectiveness of the self-supervised learning approach in improving downstream generalization. The experiments also explore the impact of subject conditioning methods on in-distribution and novel subject generalization. Overall, the method is rigorously tested through a series of experiments that showcase its ability to scale speech decoding with unlabeled data and generalize across diverse datasets, tasks, and subjects.
What results were achieved with this new method?
The new method achieved significant results in scaling speech decoding with unlabeled data. The representations learned with pretext tasks demonstrated the ability to generalize across datasets, subjects, and tasks. The method showed improvements in downstream accuracy as the amount of unlabeled data increased, outperforming baselines and supervised classifiers. The pre-training with unlabeled data significantly improved downstream generalization, even surpassing supervised baselines. The representations were able to generalize across heterogeneous scanners and tasks, showcasing cross-dataset and cross-task generalization. The method also demonstrated the ability to generalize to novel subjects, although with a slight reduction in accuracy compared to in-distribution subjects. Overall, the results indicated that the self-supervised method was effective in learning generalizable and scalable representations for speech decoding tasks.
What are the limitations or drawbacks of the method?
The limitations or drawbacks of the method outlined in the paper include the focus on only 2 downstream tasks, speech detection and voicing classification, instead of predicting full transcripts from brain recordings, the potential for more useful pretext tasks to be discovered beyond the ones presented, the emphasis on herd speech over other types like attempted or imagined speech, and the uncertainty of how much speech decoding tasks can be enhanced by scaling up the number of datasets used in training. Additionally, the method has not yet been extended to predict all English phonemes, did not explore spatial features in brain recordings, and has not conclusively demonstrated the generalization of the method to other varieties of speech beyond herd speech. Furthermore, while the paper surpasses the amount of data used in other studies, the extent to which speech decoding tasks can be improved by scaling up the number of datasets remains to be fully understood.